ਤੁਹਾਨੂੰ ਕਿਸੇ ਪਾਣੀ ਨਾਲ ਭਰੇ ਤਲਾਅ ਉੱਤੇ ਸੈਰ ਲਈ ਲੈ ਚਲੀਏ। ਸੈਰ ਪਾਣੀ ਦੇ ਉੱਤੇ ਹੀ ਕਰਾਂਗੇ। ਕਿਉਂ? ਮੇਰਾ ਪ੍ਰਸਤਾਵ ਕੁਝ ਅਟਪਟਾ ਜਿਹਾ ਲੱਗ ਰਿਹਾ ਹੈ। ਕੀੜੇ ਮਕੌੜੇ ਤਾਂ ਆਰਾਮ ਨਾਲ ਹੀ ਜਿੱਥੇ ਦੇਖੋ ਪਾਣੀ ਦੀ ਸਤ੍ਹਾ ਤੇ ਤੁਰ ਰਹੇ ਹੁੰਦੇ ਹਨ। ਫਿਰ ਅਸੀਂ ਕਿਉਂ ਨਹੀਂ ਤੁਰ ਸਕਦੇ ਪਾਣੀ ਦੀ ਸਤ੍ਹਾ ਤੇ? ਇਹ ਸਭ ਕੁਝ ਸਮਝਣ ਲਈ ਸਾਨੂੰ ਪ੍ਰੋਪਰਟੀਜ਼ ਆਫ ਲਿਕੁਇਡਸ ਦੀ ਸਟੱਡੀ ਕਰਨ ਦੀ ਲੋੜ ਹੈ। ਲਿਕੁਇਡਸ ਦੀ ਇੱਕ ਖਾਸ ਪ੍ਰੋਪਰਟੀ ਜਿਸ ਦਾ ਨਾਂ ਹੈ ਸਰਫੇਸ ਟੈਂਸ਼ਨ, ਸਾਡੇ ਇਸ ਤਰ੍ਹਾਂ ਦੇ ਕਈ ਸਵਾਲਾਂ ਦੇ ਜਵਾਬ ਦੇ ਸਕਦੀ ਹੈ। ਇਹ ਪਾਣੀ ਦੀ ਹੀ ਨਹੀਂ, ਹਰ ਇੱਕ ਲਿਕੁਇਡ ਦੀ ਪ੍ਰੋਪਰਟੀ ਹੈ। ਇੱਥੇ ਜਿਹੜਾ ਕੀੜਾ ਤੁਸੀਂ ਪਾਣੀ ਉੱਤੇ ਚੱਲਦਾ ਵੇਖ ਰਹੇ ਹੋ, ਉਹ ਵੀ ਪਾਣੀ ਦੇ ਗੁਣ ਸਰਫੇਸ ਟੈਂਸ਼ਨ ਦੇ ਕਾਰਨ ਹੀ ਹੈ। Today's lesson is going to explore a lot of knowledge about this property of water. Dear students, welcome to today's lesson on surface tension. This is the name of a common property of all liquids. Of course, its measurement varies from one liquid to another. Today, we will aim at studying this very topic. But before doing that, let me share the learning objectives for today's lesson with you. On completion of this topic, learners will be able to discuss intermolecular forces, describe surface tension and surface energy, describe the pressure difference across a curved liquid surface, describe excess of pressure inside a liquid drop and a bubble. Define capillarity and explain its applications. Discuss the rise of liquid in a capillary tube. You must have noticed that oil and water do not mix together. Mercury does not wet the glass, but water sticks to it. Oil rises up a cotton wick. Water rises up to the top of the leaves of the tree in spite of gravitation. The hair of a paintbrush do not cling together when dry or even when dipped in water, but form a fine tip when taken out of it. All these and many more such experiences are related with the free surfaces of liquids. We know that the liquids have no definite shape but have a definite volume. They acquire a free surface when poured in a container. These surfaces possess some additional energy. This phenomenon is known as surface tension and it is concerned with liquids only, as gases do not have free surfaces. Let us now understand this phenomenon. The term surface tension comes into play only when the liquid surface is in contact with the gases, which may be air. It might have been noticed by some of you that the surface of a liquid where the liquid is in contact with air acts like a thin elastic sheet. This is a result of attractive intermolecular forces among the molecules of substances. Let us first know about the intermolecular forces. Intermolecular force stable molecules ਵਿਚਕਾਰ ਕੰਮ ਕਰਨ ਵਾਲੀ force of attraction ਹੁੰਦੀ ਹੈ। ਇਹਨਾਂ molecules ਵਿਚਕਾਰਲੀ gravitational force ਬਹੁਤ ਹੀ ਜ਼ਿਆਦਾ weak ਹੁੰਦੀ ਹੈ। ਇਸ ਕਰਕੇ gravitational force ਕਾਰਨ ਤਾਂ molecules ਆਪਸ ਵਿੱਚ ਬੱਝੇ ਨਹੀਂ ਰਹਿ ਸਕਦੇ। molecules ਨੂੰ ਇੱਕ ਦੂਜੇ ਨਾਲ ਜੋੜ ਕੇ ਰੱਖਣ ਵਾਲੀ ਇਹਨਾਂ ਵਿਚਕਾਰ electric interaction force ਹੀ ਹੈ। पर ਇਹ force सिर्फ short distances ਲਈ ਹੀ ਕੰਮ ਕਰਦੀ ਹੈ। So, ਇਹਨਾਂ ਦਾ ਨਾਂ short range forces ਰੱਖਿਆ ਗਿਆ ਹੈ। The maximum distance up to which a molecule can attract some other molecule is known as the range of the intermolecular force. However, we have two types of intermolecular forces, namely cohesive force and adhesive force. An intermolecular force of attraction between the molecules of the same type is known as the cohesive force. The molecules of a water droplet are held together by cohesive force. On the other hand, the intermolecular force of attraction between the molecules of dissimilar type is known as the adhesive force. Some examples of adhesive forces are: paint sticks to metal surface due to large adhesive force between the surface of metal and the paint molecules. The force of adhesion between the lubricating oil and the parts of a machine also plays an important role in avoiding the wear and tear of the machine. The use of cement and bricks in construction work is possible due to the presence of large adhesive force between the cement and the bricks. We will now define the surface tension. Surface tension is that property of a liquid by virtue of which it behaves like an elastic stretched membrane with a tendency to contract so as to occupy a minimum surface area. As an example, a water drop falling from a dropper is spherical in shape, and this shape acquired by the water drop is due to surface tension. Let me elaborate this. A liquid drop is spherical in shape, which is due to the fact that for a given volume, a sphere has the least surface area, and the surface of every liquid always has a tendency to have least surface area. In this respect, the surface of the drop behaves like a stretched membrane. This is how the shape of a liquid drop comply with the definition of surface tension. To measure the surface tension, let us consider a soap solution kept in a confined region. From one of the edge of length L of the region, an imaginary line is traced passing through a point on PQ. The force F is acting inward perpendicular to the edge of the region. Now, in order to increase the region of the stored solution, an external force is applied normal to the free edge PQ. Let this free edge PQ be shifted to RS after a short displacement x. In shifting the free edge, the work is done in increasing the surface area of the liquid, which is directly proportional to the area of the region holding the soap solution. Therefore, we have work W as directly proportional to the increase in area of the region A. This implies W is equal to twice sigma into A as equation 1. Here, sigma, the constant of proportionality, is a measure of surface tension of the liquid. From equation 1, we have sigma is equal to W by A, which is equal to F into 2x upon 2L into x, which is equal to F upon L as equation 2. From equation 2, we conclude that the surface tension of a liquid can be measured as the force per unit length on an imaginary line drawn on the liquid surface, which acts perpendicular to the line on its either side at every point and tangentially to the liquid surface. Surface tension is expressed as dyne per centimeter in CGS system and Newton per meter in SI system. Since surface tension is measured as force per unit length, its dimensional formula is ml0 T minus 2. We know that the free surface of a liquid always has a tendency to contract and possess minimum surface area. So, if it is required to increase the surface area of the liquid, work has to be done. This work done is stored in the surface film of the liquid as its potential energy. Therefore, the definition goes like this. The potential energy per unit area of the surface film is called the surface energy. Or it may also be defined as the amount of work done in increasing the area of the surface film through unity. Mathematically, the term surface energy can be expressed as surface energy equal to work done in increasing the area of the surface by increase in surface area. The surface energy and surface tension are closely related to each other. Let's see how. Consider a rectangular frame ABCD made of a wire. Let us take some soap solution in a petri dish. Now, dip the wire frame in the soap solution so that a film is formed over the frame. Due to the surface tension, the film will have a tendency to shrink, and thereby the crosspiece PQ of length L present in rectangular frame ABCD will be pulled in an inward direction. However, the crosspiece can be held in this position under a force F, which is equal and opposite to the force acting on the crosspiece all along its length due to surface tension in the soap film. We know that surface tension of a liquid is the force per unit length on an imaginary line drawn on the liquid surface if T is the force due to surface tension per unit length, then F is equal to T into 2L. Here, L is the length of the crosspiece PQ. Since the film has two free surfaces, that is, on both the sides, the length of the crosspiece has been taken as 2L. To increase the area of the confined region of the soap film, an external force F is applied normal to the free edge PQ. Due to this external force, let the free edge PQ be shifted to RS after a short displacement delta x. Therefore, due to the external force F, increase in area of the film is delta A equal to 2L into delta x, and the work done is given by delta W equal to F into delta x. Substituting the value of F equal to T into 2L, we get delta W equal to T into 2L into delta x, which is further equal to T into 2L into delta x. Surface energy is equal to work done in increasing the area of the surface upon increase in surface area, which is equal to delta W upon delta A, which we will call as equation 1. Using the values of delta W upon delta A in equation 1, we get surface energy as equal to T into 2L into delta x by 2L into delta x, which is equal to T. This expression shows that the surface tension of a liquid is numerically equal to its surface energy. What would be the exact shape of the liquid surface? That depends upon the pressure difference. The surface of a liquid may be concave, convex, or plane. The force due to surface tension on the molecule M in the surface of the liquid acts tangentially to the surface in all directions. Consider a molecule M on a concave meniscus of a liquid. Then, due to the surface tension, molecule will experience a net outward force normal to the surface. The liquid molecule will remain in equilibrium if the pressure on the concave side of the liquid is more. If the liquid surface is convex, then due to surface tension, the molecule M will experience a net inward force normal to the surface. The liquid molecule will be in equilibrium if the pressure on the concave side of the liquid is more. If the free surface of a liquid is a plane surface, the molecule M is pulled equally in all directions and experiences no net inward or outward force. Thus, there is no extra pressure on the two sides of a plane liquid surface due to the surface tension. It should be clear now that a curved surface is in equilibrium only if there is an excess pressure on the concave side of the curved surface. We know that a liquid surface possesses minimum surface area by virtue of surface tension. Small drops and bubbles of liquid possess spherical shapes due to the fact that they have negligible effect of gravity on them. However, a big drop of liquid is affected by gravity, and hence its shape is flattened. Due to their spherical shapes, small drops of liquid must possess minimum surface area. Also, a liquid drop or a liquid bubble does not collapse under the effect of the force of surface tension. This simply means that the pressure inside the liquid drop or the liquid bubble must be greater than that outside it. Let us now determine the mathematical expression for pressure inside a liquid drop. Let us consider a liquid drop of surface tension T and radius r. Let Pi and Po be the pressure inside and outside the drop of the liquid. Then excess pressure inside the liquid drop is delta P equal to Pi minus Po. Let the radius of the liquid drop increase from r to r plus delta r due to this pressure difference, so that the increase in the radius of the liquid drop is delta r. If F is the force acting on a body of the surface area A experiencing a pressure P, then F is equal to Pa. Thus, the outward force acting on the liquid drop is Fo equal to Pi minus Po whole into 4 pi r square, and the small work done in order to increase the radius of the spherical liquid drop to delta r is delta W equal to Fo into delta r. Using the value of Fo, we can write delta W equal to Pi minus Po whole into 4 pi r square into delta r, which is equal to 4 pi r square into whole of Pi minus Po into delta r, representing equation 1. This work, delta W, is experienced by the excess of pressure against the force of surface tension, and this work is stored inside the liquid drop in the form of its potential energy delta U. Thus, potential energy of the liquid drop increased by delta U is equal to surface tension into increase in surface area. Since due to the experience of excess pressure by the spherical liquid drop, the radius of the spherical liquid drop increase from r to r plus delta r, due to which the increase in surface area is delta A equal to 4 pi into r plus delta r whole square minus 4 pi r square, which is equal to 4 pi r square plus 8 pi r delta r plus 4 pi delta r square minus 4 pi r square. This implies delta A is equal to 8 pi r delta r plus 4 pi delta r square as equation 2. Substituting the value of surface tension T and increase in the surface area delta A from equation 2 in the expression for delta U, we get the increased potential energy of the liquid drop as delta U equal to T into whole of 8 pi r delta r plus 4 pi delta r square. As delta r has a very small value, delta r square is nearly equal to 0. This implies delta U is equal to 8 pi RT delta r as equation 3, representing the increased potential energy of the liquid drop. We know that this increased potential energy is equal to the work done delta W equal to 4 pi r square into whole of Pi minus Po into delta r in order to increase the size of the spherical liquid bubble. It can thus be written as 4 pi r square into whole of Pi minus Po into delta r as equal to 8 pi RT into delta R. Simplifying this, we get Pi minus Po equal to 2T upon R. This relation represents the excess pressure inside a liquid drop. Similar to the liquid drop, the excess pressure inside an air bubble is also given as Pi minus Po equal to 2T upon R. Then, the excess pressure inside liquid bubble can also be calculated. Remember that in a liquid drop, the liquid is inside the drop and air is outside. Whereas, in a liquid bubble, the liquid is outside the spherical core of air. Thus, a liquid bubble has two free surfaces as there is air both inside and outside it. Therefore, the excess of pressure inside a liquid bubble is calculated to be Pi minus Po equal to 4T upon R. I will now like to introduce one more important phenomenon due to surface tension, which is known as capillarity. A tube of very fine bore is called a capillary tube. In other words, a tube whose bore is as thin as that of a hair strand is called a capillary tube. When a capillary tube of glass, open at both ends, is placed vertical with its lower end immersed in water, the water is observed to rise in the tube. When the same capillary tube is dipped in a liquid, say mercury, which does not wet the walls of the tube, the liquid depresses below the free surface of the liquid in the container. Rise or fall of liquid in a capillary tube is called capillarity or capillary action. The extent to which a liquid rises or depresses depends upon the radius of the bore of the tube. It has been found that narrower the bore of the tube, greater is the rise or fall of the liquid in the tube. Let me show you some practical applications of capillary action. Oil rises in the cotton wick of a lamp through the small capillaries formed by the threads of the wick. The tip of the nib of a pen is split to provide capillary action for the ink to creep in. Due to capillary action, water rises to the surface of the soil in the fields and gets evaporated. Moisture rises in plants by capillary action. It is the capillary action due to which the water reaches every branch of a plant or a tree through the stalk. Earthen vessels are used in summers to provide cold water. The pores of the earthen vessel act as capillaries. The water oozes out, gets evaporated by taking heat from the earthen vessel and cools the remaining water in the vessel. We know by now that when a liquid comes in contact with a solid surface, it is generally curved. Let us imagine a liquid molecule common to both the liquid surface, that is, in contact with a solid, and the liquid free surface. There are cohesive and adhesive forces, Fc and Fa respectively, acting on this molecule. As a result, the molecule will exert a resultant force F. When Fa is greater than Fc, the liquid would wet the solid surface and the meniscus of the liquid surface becomes concave near the solid plane. However, the contact angle theta would be less than pi by 2. When Fa is less than Fc, liquid does not wet the solid surface and its meniscus becomes convex near the solid surface. However, the contact angle theta would be greater than pi by 2. The angle of contact for pure water and clean glass surface is 0. Therefore, in a clean glass tube, the meniscus of water will be exactly hemispherical. For ordinary water and glass, the angle of contact is about 8 degrees, while For mercury and glass, the value is 140 degrees. It may be noted that for a given liquid-solid pair, the angle of contact is the same whether the liquid is contained in a vessel made of that solid material or a rod of that solid material is dipped in this liquid. Knowing the angle of contact, we can discuss the phenomenon of rise of liquid in a capillary tube. Consider a capillary tube of radius r, open at both ends and dipped into a liquid which wets the walls of the tube. The angle of contact for such a liquid will be acute and hence the meniscus will be concave. Let theta be the angle of contact and T be the surface tension of the liquid. The liquid surface is in contact with the walls of the tube all along the circle of circumference where C is equal to 2 pi r and r is the radius of the tube. Due to surface tension of the liquid, a force T acts inwards along the tangent to the meniscus per unit length of the tube. Since the liquid surface has a tendency to contract, it pulls the tube inward all along the circumference of the circle of contact. Thus, the liquid exerts a force T per unit length on the glass tube, and hence on applying the concept of Newton's third law of motion, we observe that the tube gives an equal and opposite normal reaction R to the liquid. Thus, the normal reaction R, which is equal to the surface tension T, acting at each point along the circle of contact, can be resolved into two components. One of the components is T sin theta per unit length along the horizontal, which acts radially outwards along the circle of contact. These components cancel the effect of each other. The other component is T cos theta per unit length along vertical in the upward direction. Thus, the total upward force on the liquid Fv is equal to 2 pi r into T cos theta. Due to the upward force Fv, the liquid rises in the tube to a height, say h, till the weight of the liquid above the free surface becomes just equal to the vertical upward force. Hence, weight of the liquid above the free surface in the container is equal to the volume of liquid in the tube up to height h plus volume of liquid in the meniscus whole into rho g. Now, if the meniscus is hemispherical in shape, the weight of the liquid above the free surface is equal to the volume of liquid in a cylinder of radius r and height h plus volume of liquid in a cylinder of radius r and height equal to r minus volume of a hemisphere of radius r whole into rho g. Mathematically, this can be written as WLA equal to pi r square h plus pi r cube minus 2 by 3 pi r cube whole into rho g, which is equal to pi r square into whole of h plus r by 3 whole into rho g as equation 1. Since for equilibrium, total upward force is equal to weight of the liquid above the free surface, which gives us an equation that is 2 pi r into T cos theta equal to pi r square into whole of h plus r by 3 into rho g. This implies T is equal to r rho g into whole of h plus r by 3 divided by 2 cos theta as equation 2. If the tube has a very fine bore, its radius may be neglected as compared to h, or r by 3 be nearly equal to 0. Applying this to equation 2, we get the surface tension T as equal to r rho g h upon 2 cos theta. Also, the height h to which the liquid rises in the tube is given by h is equal to 2t cos theta upon r rho g. This equation is also called as ascent formula. From the ascent formula, we can deduce that the height h to which a liquid rises in the capillary tube is inversely proportional to the radius of the tube, inversely proportional to the density of the liquid, directly proportional to the surface tension of the liquid. This equation makes it clear that the capillary rise is due to surface tension. It is larger for a smaller radius of the capillary. It is of the order of a few centimeters for fine capillaries. Please notice that if the liquid meniscus is convex, as in case of mercury, that is, if cos theta is negative, then the liquid will be lower in the capillary or vice versa. Well, it's now the time to conclude the topic for today. May we have a quick look at the important points from it. Surface tension is that property of a liquid by virtue of which it behaves like an elastic stretched membrane with a tendency to contract so as to occupy a minimum surface area. Surface energy is the potential energy stored in the surface film, which is equal to work done in increasing the area of the surface by increase in surface area. The excess pressure inside a liquid drop is given as Pi minus Po equal to 2T upon R. The excess pressure inside a liquid bubble is given by Pi minus Po equal to 4T upon R. The excess pressure inside an air bubble is calculated to be Pi minus Po equal to 2T upon R. The height to which the liquid rises in a tube is h equal to 2T cos theta upon R rho g. This given formula is known as ascent formula. May I now ask you some questions so as to make you feel confident with the concept of surface tension. The first question is, what is the relation between the surface tension and surface energy? The answer is, surface tension is equal to surface energy, which is equal to work done in increasing the area of the surface by increase in surface area. The next question is, name the phenomenon by which the water rises from roots to leaves of plants. And the answer is, it is the capillary action by virtue of which the water rises from roots to the leaves of plants. The next question is, define angle of contact. The answer is, it is the angle between the tangents to the free surface of the liquid at the point of contact and the wall of the container when measured inside the liquid. मैं आस रखदी हां कि ਤੁਸੀਂ ਸਰਫੇਸ ਟੈਂਸ਼ਨ ਨੂੰ ਚੰਗੀ ਤਰ੍ਹਾਂ ਜਾਣ ਅਤੇ ਸਮਝ ਲਿਆ ਹੈ। ਰੋਜ਼ਾਨਾ ਜੀਵਨ ਵਿੱਚ ਆਪਣੇ ਆਸ-ਪਾਸ ਇਸ ਦੇ ਹੋਰ ਉਦਾਹਰਣ ਲੱਭਣ ਦੀ ਕੋਸ਼ਿਸ਼ ਕਰਦੇ ਰਹੋ ਤਾਂ ਤੁਸੀਂ ਇਸ ਨੂੰ ਹੋਰ ਵੀ ਚੰਗੀ ਤਰ੍ਹਾਂ ਸਮਝ ਸਕੋਗੇ। ਪਾਠ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਇੱਕ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ।